Hello, and welcome to another edition of Math, Music, and More. I got a lot of ground to cover today, so I know some of you have complained in the past in the comments that I talk too slowly, so I'm going to try to pick up the pace today. I got a lot to cover, and I hate using scripts. I like doing everything sort of off the cuff. But in this case, there was so much to do. I don't have a script, but I at least have an outline. So I'm going to walk through first, very quickly, all the different topics I'm going to cover in just today's episode. And if some of this stuff you already know, you can just skip forward to each point where I'm sort of crossing it off. Done, done, done. And what's really the crux of the matter here? It's all about finally introducing not only the notion of uncountable infinity and how it actually exists, but that it in fact represents the size of all real numbers. And I want to arrive at a proof that I just sort of did on my own last night because I just felt like it. I could just try to recant things that other great people have done, but that's kind of boring. I mean, you can look that up for yourself. I rather sort of come up with my own way of thinking. And I suggest all of you, especially in the theoretical math world, it's always good to think for yourself and just get creative. So let's go through the outline. Point number one, I'm going to go through bijectivity again. I'm going to clarify a little bit illustratively exactly what it means, and then I'm going to talk about why we actually need to have such bijective mappings. Number two, we're going to talk about repeating decimals, because as you know, as soon as it's repeating, it's no longer irrational, it's rational, and I have some things to say about that. Then I'm going to talk about this number here called 10 to the infinity. And when I say infinity here, I'm specifically referring to countable infinity and why that number matters to me. Then I'm going to create a false bijective mapping. I'm going to create a mapping where I can show that this is not bijective and talk about what the implications are. And then I'm actually going to get into the proof, and it's going to be all around assignments and differences. And I'll explain what I mean by that later. And then finally, as I always like to do, there's always some sort of general insight. Isn't it interesting, this relationship between algorithms of finite steps and countable infinity? And you can probably guess what the next step is going to be: countably infinite steps, and the release, therefore, to uncountable infinity. So let's jump right into it. Bijectivity. As you remember what bijective means, it means that a mapping is both surjective and injective. Usually people say things in the other order, but I'm going to use an illustration to denote exactly what that means. Let's say we have a set here A, and let's say we have a set here B, and we have 4 points, and here we have 4 points. Notice how if we just look at the points, which are supposed to represent the elements in the set, these two sets look like they're the same size, and in fact they are. Because we could create a mapping from this point to this point, from this point to this point, from here to there, and then finally also from here to here. First, I'm going to talk about the notion of injectivity, in other words, one-to-one. Remember how we said not only does a function have to be such that for every x there's one and only one f of x, we also said that for something to be one-to-one, in other words, injective, for every one here, there has to be only one there. Let's just draw a quick illustration of what that means and why it's important. What if I had a point here and a point here, and both of these points mapped to here? Do you see how right away you can see there's 6 elements in this set and only 4 elements in that set? They're clearly not the same size. So that to me is a great illustration as to why injectivity or one-to-one is so important. Next, let's talk about surjectivity or onto. And you can probably guess how this is going to look. This is supposed to be 4 elements to 4 elements again. What if we just had a bunch of other elements here? Here you can see that the mapping, the function, maps 4 to 4. But there are here in this example 5 other points that have not been reached by this mapping. Clearly 4 does not equal 9. This is why surjectivity or onto is so important. And hence I just thought, giving a quick illustration really strengthens our intuition as to why bijectivity matters so much. So that's point number one. Point number two, I'm going to claim that you have to have a bijective mapping to actually demonstrate the two sets are the same. Because if I have elements over here and elements over here, and I don't have sufficient information, and therefore without the sufficient information, an ability to even create a mapping between the two, then I have no way of knowing if they're actually the same size or not. This is of paramount importance, the need, the necessity of a bijective mapping to talk about the size or the measure of any kind of set. Because the thing that I'm going to do is I'm going to get into uncountable infinity, and I want to demonstrate that there is no bijective mapping. And if there is no bijective mapping between the natural numbers and the real numbers, or the irrational numbers for that matter, then it must be uncountably infinite. So I just want to make sure that's clear, that necessity for a bijective mapping. Now we can finally say This one is done. So let's move on to repeating decimals. This could be something that's incredibly elementary and rudimentary for all of you. So forgive me, and again, skip if you think this is too easy, but I'll just give you an example. We could have 0.1111111 going to infinity, right? That's obviously equal to 1/9. That is a repeating decimal. So clearly it's a rational number because I even denoted it here as an m over n, where m and n are integers. But notice that I could go out and just change one of the digits and then keep going to infinity. Is that a rational number? Let's think about it. Because we could change it again. We could say it's 13131111. If I kept doing that, would that still be a rational number? And the answer is yes, because all we have to do is break something like this up into pieces. So for example, this portion right here is nothing more than 13/100ths, and this portion right here is nothing more than 1/9 times 100, so 1/900ths. And you can guess that this one is kind of similar. It's like 1313 over 10,000, whereas this would be 1/9, I think, times 10,000. Correct me if I'm wrong. So it's, again, the sum of two rational numbers, and the sum of any two rational numbers is also a rational number. So I just want our intuition to really lock into that, hey, you know what? Whenever you have a repeating decimal, it doesn't matter how long it takes to get to that repeat. If it repeats at some point, we can break that thing up into components, each of which are rational, and therefore the sum of all the rationals is still a rational number. That's going to be important in our distinction later between the irrationals and the rational numbers. So now I'm going to talk about this notion of 10 to the infinity. But because I'm OCD, before I do that, I of course have to cross that off. So why did I even bring up the notion of 10 to the infinity? If I constrain for a moment the space that we're looking at, a subset of the rational numbers, to just those that are expressed as decimals of 0 point something, you could say that 0 point digit, they're all kinds of digits. And how many digits do you have? Well, you have a countably infinite number of digits. And how many entries could you have in each of those spaces, each of those placeholders? Well, it's anywhere from 1 to 9. And therefore, the number of different combinations you have is actually, because 0 to 9, not 1 to 9, would be 10 different entries. And then you have 10 to the infinity different options, just looking at decimals. That's it. And it includes the ones that terminate, of course, because you could have 0.05, 0.00000, or you could have ones that actually go on forever, such as 1/9 or any kind of combination of those numbers. So this is why I think 10 to the infinity is such an important number that we're going to focus on here. Next point, I'm already almost at 8 minutes, so I should talk faster. A false bijectivity. We could try to create a bijective mapping F between the natural numbers and this subset of the real numbers, which I will call R sub s. I'm just calling it that. And this functional mapping could be something like, well, let f of each element of the natural numbers n just be simply 10 to the n. And you know what? I'll make it negative since we're talking about everything going out in that direction, right? So for example, 10 to the 1, or if we consider this to be whole numbers instead of just natural numbers, 10 to the 0 would just be 1, but we're actually just looking at decimals. 10 to the negative 1 would just be 0.1. 10 to the negative 2 would be 0.01. 10 to the negative 3, 0.001, and so on and so forth. And we could claim that this is an actual function, which is true, and we could claim that it's actually injective, because for every value here, there's only one and only one n that actually maps to that. But there's no way in bleep that this is actually surjective. Because think of all the different numbers that are not being covered between 0.1 and 0.01, right? And not only that, but there are lots of numbers that don't have ones in the digit places. So this is clearly not surjective. Therefore, this is not a bijective mapping, which is a true statement. And therefore, the real numbers must be uncountably infinite. That's the mistake. I didn't actually prove that yet. So why is that a false bijectivity proof? It's because all I proved is that this one function is not bijective. Wow, that makes everything a lot more complicated, because it means proving that one mapping is not bijective isn't enough. We have to somehow prove that there exists no mapping from the natural numbers to this subset of the real numbers. So this is where we get into the proof. And this is, again, my version. So I very much welcome criticism or how it could be formalized, because I was actually told by AI that it's very similar to the Georg-Cantor proof, but I don't want to go into that because then I'm just rehashing someone else's thinking. What I was thinking is that, as I noted before, every single rational number can be created through a finite number of steps. You change this digit, you change that digit, you can change it into 2 fractions, 4 fractions, whatever number of fractions you want, and then you can simplify it. But there are numbers that never have a repeating pattern, no matter how far out you go. And those are those irrational numbers, right? So that's what's interesting about it, because if you have all these digits that go out to infinity, and they never, ever, ever repeat, that means there are an infinite number of steps you would have to take to even define one irrational number. We could come up with a finite number of steps to define this irrational number out to the 15th place. But if you really want to define an irrational number in decimal form in its entirety, it actually takes a countably infinite number of steps. Step, 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 step. So here's the problem that I have. Remember how we talked about the necessity for a bijective function? We have to demonstrate that it's both injective and surjective. Well, certainly this could be surjective, but how do we prove that it's injective, that it's actually a function and that there's always only one value of n that drives there? We would have to be able to create one of these and then create another one and demonstrate that they're actually different. We have to be able to subtract the two to demonstrate that they are in fact unique irrational numbers. Means that we have to be able to calculate the difference. But here lies the rub, because it takes a countably infinite number of steps to even create in its entirety an irrational number. And if that happens, that means you can never actually calculate in its entirety what the differences are between incredibly close irrational numbers. Anytime they get close, if you can actually calculate it, I can always pick one that's closer and closer and closer, and you'll never be able to determine the difference. And if you can't determine the difference out to infinity, an infinite number of places for two, comparative purposes, irrational numbers, that means we can never actually create a bijective mapping, because we can't prove that that mapping is both injective and surjective. Hence,